Hello and welcome to this Megit webinar on functional safety. Functional safety importance is increasing every day and for a very good reason, the protection of human life. My name is Ricardo and I will address today some basic aspects of functional safety, reviewing what it is and what it means. We will look very briefly into the functional safety standards, in particular IEC61508, and also into the certification process and on what it means to be SIL certified. After that, we will discuss the most important terms and abbreviations and see some examples of SIL certificates. Finally, we will discuss some myths, truths, and common questions about functional safety. To better understand what is functional safety, let's start by looking into a practical example that, though not in the scope of IEC61508, will help us to understand functional safety philosophy. Imagine that you are in the situation shown in this picture. As you can guess, some safety elements are required to protect the climber in case he cannot hold grip anymore. So, first thing we need to understand is the risk to which we are exposed and also the consequences of an accident. Clearly, the risk factor that comes to my mind is height. But there are others. How does the landing zone looks like? For how long I will need to sustain my grip? Also, how often I expect to resort to the safety gear? Is it something that I will use every time to descend, for instance? The evaluation of the risk to which I am exposed will dictate the level of protection I will need. As we will see later, this evaluation will tell me what SIL level I will need for my application. Now that we know the risks, let's look into the risk reduction measures that I can put in place and how strong they are to lower my risk. For that, we need to think about what can go wrong with them. There are several things that can go wrong. For example, a design or a manufacturing issue. We can also have a latent defect or some random fault that will prevent the safety system to work properly. Another crucial aspect that I must consider is, am I using my safety gear properly? Is the safety gear appropriated to my case? Is it well documented? All these questions relate to the effectiveness of my risk reduction measures. As we will see, this means the SIL level I can attribute to my safety gear. So, what we have just discussed are safety fundamental questions. Let's see how all these aspects translate into functional safety. Let's start by risk. As we hear often, there is no such thing as zero risk, but there is for sure a notion of acceptable or tolerable risk, and we apply this notion of acceptable risk every day in our life. However, as you know as well, each one of us has a different perception of risk. Therefore, the safety standards provide us clear indications on how to calculate it. This is done based on consequences, frequency and exposure time, and probability of non-avoidance. It also takes into account how much I will rely on the safety measures, that is to say, how often I will trigger the safety function. Based on these parameters, and with the help of different methods provided by the safety standards, we can find out the amount of risk we are talking about and what risk reduction measures effectiveness one needs to put in place to lower the risk to accepted levels. In fact, functional safety standards are all about risk reduction measures that need to be put in place to reduce risk and protect persons, and in a more wide sense, assets, environment, reputation, and liability. The safety instrumented systems that we will address during this safety function presentation are only one of the independent safety layers that exist. In fact, safety relies on a set of different independent layers that go from risk control and reduction to risk mitigation. The risk reduction measures effectiveness is translated into accepted probability of failure and ultimately into the IEC61508 SIL levels that we hear about. For example, if based on my risk analysis I must reduce risk 500 times in order for it to be acceptable, my safety instrumented system must comply with SIL 2. Okay, so now that we know how to find out what SIL level we need, let's see how we can evaluate risk reduction effectiveness, that is to say, the SIL level my safety instrumented system can give me. For that, let's remind the type of faults we have identified in our example. These failures can be classified into two distinct groups. We have failures that are considered systematic, such as design issues, also systematic manufacturing issues, and others. We have also failures that are clearly related with random events. It means failures occurring at a random time, which result from a variety of degradation mechanisms or random external influences. These two aspects are taken into account via different methods in the safety standards, and will dictate the amount of risk reduction that is provided by a particular device, in terms of systematic faults and also random faults. Note that we need these two aspects to be considered. I must prove that my device has low probability of failure, but also that the possibility of having systematic errors is as well minimized. Apart from risk and failure, that can be random or systematic, as we see, we have also the last question. Am I using my safety gear properly? Is it appropriated for my case? These questions are of course also covered by the functional safety standards. In particular, for IEC61508, the architectural constraints are well defined, and it also requires to have a very complete safety manual to make sure that the system is well applied. To summarize, functional safety evaluates risks and hazards, and also the performance of the risk reduction measures. In particular, IEC61508 ensures that the safety functions of the devices are correctly performed. It also ensures that, in case of failure, the safety device, the system, will fall into a predicted safe state. Note that while other standards, like electrical safety, focus on, let's say, static properties of the devices, functional safety focuses more on the dynamic properties of the systems, that is to say, on the function executed by these systems. IEC61508 contains requirements for manufacturers of suppliers of electrical, electronic, and programmable electronic safety-related instruments. These requirements are designed to ensure that the safety systems can provide the required safety integrity level across the entire product lifecycle, from development to decommissioning. Note that there are many other functional safety standards that, contrary to IEC61508, are much more application-specific, like for industrial processes, nuclear power, and so forth. But since IEC61508 lists functional safety requirements that must be observed by manufacturers or suppliers of safety-related systems, it is considered the basic standard for functional safety. All other functional safety standards will relate, one way or another, to IEC61508. The IEC61508 standard covers the entire life cycle of a safety-related system, from conceptualization to decommissioning, passing by, of course, specification and development phases and system validation. The first set of requirements relate to the conceptualization of the safety system. One or more use cases must be identified and the hazards and risks associated to these use cases be analyzed. In some cases, especially when we talk about elements and not entire safety systems, we know already the SIL target that we want to achieve. In that case, some of the risk and hazard analysis won't be necessary. However, we must be really sure that the SIL level chosen for a certain element fits the application and the market expectations. Then we have the requirements for the realization and validation phases. And this is where most of the things happen. The realization phase is divided into hardware and software and includes the definition of techniques and measures that are required to make sure that design meets the chosen safety integrity level. The last set of requirements relate to operation, maintenance, and decommissioning. There is a high focus on the entire operational life cycle of the system in this part of the standard. It means, for example, that during the life of the product, the supplier must look at all reported faults and introduce them into the safety analysis to evaluate constantly if these field failure factors are impacting the initial safety assumptions or not. These phases cover as well decommissioning. And this is important because an obsolete system may not be safe anymore, so it must be clear to the user how to proceed when the product reaches the end of its operational life. Starting from the technical requirements framework, the standard further refines the activities with more detail. Since all life cycle of the safety system is covered, it is normal that some parts are more related with the application itself and others with the development of elements or safety-related systems or subsystems. So, functional safety, and in particular IEC61508, covers the entire life cycle of safety-related system and aims to protect us from technology. Let's take a look now into the functional safety assessment and certification process. We will focus our attention on phases 9 and 10 of the safety life cycle. These phases are related with the specification and realization of safety-related systems or elements that you will use to construct your safety instrumented system. Before looking further into the certification process, let's remind the meaning of SIL level. We know already that the SIL tells us how good our system performs in terms of safety, or in a way how well it reduces risk. The higher the SIL number, the higher the risk reduction. In other words, the higher the number, the better the safety system will manage risk. Getting back to our certification process, to be compliant with a certain SIL level, the system needs to respond to three major aspects. The first one is systematic capability. This is all about quality system. The systematic capability requirements ensure that the quality management system, the design and development processes, etc., are sound enough to mitigate systematic errors. The systematic capability represents very well the level of quality of the processes and management of safety in a company. Second one is the probability of failure. The probability of failure is calculated based on the failure rates of the system, combined with timing parameters accordingly to the implemented architecture. The failure rates themselves are obtained via a FMEDA, failure modes, effects, and diagnostic analysis. The higher the SIL level, the lower the probability of failure must be. Finally, we have the architectural constraints. Architectural constraints relate to the robustness of the system and are an additional certification barrier that is put in place to avoid too optimistic results obtained from probability of failure calculations or from field reliability data analysis. For example, the calculation of the probability of failure can be biased by unrealistic parameter values such as a very short proof test time intervals. To avoid these artifacts, some architectural constraints are put in place and dictate a minimum hardware fault tolerance in the safety system depending on the SIL level intended for the application. We can only certify a system if all these three aspects are validated. So certification process goes beyond a well-designed system or a good development process. It is the conjugation of best practices on all these areas that will dictate the success or not of a certification. In very practical terms, the SIL certification process can be summarized into three crucial parts: the systematic failures, the random faults, and a solid safety manual. Note that the architectural constraints are basically limitations imposed on top of this systematic and random fault analysis. Therefore, they don't appear directly in this representation. As you can see, there are two certification options, by design or by proven in use. The major difference is on the systematic failure integrity evaluation. While in a certification by design, the evaluation of the quality system and design processes will tell me how far systematic faults are avoided, in a certification type proven in use, the systematic failure integrity is evaluated by observing field reliability data. Of course, this assumes that there is enough field data with high level of statistical confidence, and also that there is a sound enough quality system that manages this data. Architectural constraints will be different for proven in use certification. So the same physical equipment may have different safety properties depending on the type of certification it went through, by design or by proven in use. Certification process is based on the assessment of different documents and evidences of appropriate systematic failures and random fault avoidance. Note that the assessment will be done on the product, but also on the tools that are used to design it. And it will also take a deep look into the way the product is tested and even in the way the product is manufactured. Of course, this means that a very comprehensive set of documentation and evidences must be prepared to pass a certification. The level of independency of the assessor or assessors depends on the SIL level. The higher the SIL level, the more independence we will have to have. For example, while for a simple SIL 1 device we will only require one independent person, for SIL 4 we will need to have an independent external organization assessing the compliance with safety requirements. For example, an independent person, part of the development team, would never be accepted. SIL 3 requires an independent external organization to perform the assessment. However, if the safety system is simple enough, or if there is proved expertise, the standard allows us, in this case and under justified basis, to do the assessment with an independent department within the company. Note that here we are talking about the assessment part of the certification. The SIL certificate itself can only be issued by a certified body. At Megit, the SIL assessment is complemented by an external third-party assessment prior to certification. Additionally, the departments are regularly audited by different external entities to ensure that the safety standards are always met. Now that we know the philosophy behind functional safety and a bit more about functional safety standards and the associated certification process, we can discuss what it means for a product to be certified. When you are building your safety instrumented system, you must have confidence on the elements you are using. Most of the times you are using well-known devices from reputed companies. In this case, you can simply request reliability data to your supplier and perform your own safety calculations. But sometimes you need some more formalism, either because reputability of the device is not established or because there are stronger SIL requirements, technical or legal, behind. In that case, you will benefit from choosing a certified product, because it will mean that safety properties of the element were properly validated. It also reassures you that your supplier has a good quality system and that you will have access to a complete safety data that is crucial to construct a properly designed safety instrumented system. There are some specific terms and abbreviations related with functional safety that you should be aware to better understand it. Starting by the top-level definitions, we have the Safety Instrumented System, SIS, that will execute one or more safety instrumented functions, SIF. Then we have two of the most important terms in functional safety that, if well understood, will eliminate a lot of confusions. I'm referring to the safety function and to the safe state. The first one is the safety function, and it will tell you what the safety system must do in normal operation. It will also tell you what are the safety inputs and outputs associated with it, because you can have, in the same device, several functions, several inputs and several outputs. But you need to know which ones are safe. Second one is the safe state. This is how the safety function will react when it detects a problem to put your system into a state where the hazard is removed. Now, note that the safe state can be achieved in two ways, either by normal operation of the safety function, or because there is a dangerous failure in the safety system itself that is detected by internal diagnostics. If that happens, the system will force the safe state, because the safety function cannot be assumed anymore. So, as you can see, this raises a concern about availability that we need to be aware. This is a characteristic that is given by the spurious trip rate value. This value is equal to the sum of safe and dangerous detected failure rates that we will see later. Then we have SIL and systematic capability that we have already briefly discussed. We already saw the meaning of SIL. It is an indication of the risk reduction performance that can be obtained via safety-related system, and the systematic capability that provides the level of confidence about systematic safety integrity. Both levels go from 1 to 4, being the highest the safest. Another important definition in functional safety is the demand mode. We have three modes: low demand, high demand, and continuous mode. A safety system operating in low demand is expected to be called for action less than once per year. More than that, it will be operating in high demand mode. And if the safety function is responsible for maintaining the safe state as part of normal operation, then it will be seen as operating in continuous mode. Note that these modes are related to the application. It means that the same device can eventually be used in different modes. However, the safety properties for example the imposed architectural constraints, will differ depending on the mode the device will be used. For example, a device may be used alone for SIL2, low demand, but if we wish to use it in high demand, we may be forced to have two devices in parallel. Hardware fault tolerance, HFT, simply means how many hardware faults the system can tolerate while still being able to execute its safety function. A HFT of 1, for example, means that even in the presence of one hardware fault, it will still work. You can think of it like redundancy, but be careful because technically it is not exactly the same thing. Talking about architecture, we have also the notion of M out of N channel voting architectures. This means that we have a system composed by N devices, executing the same function, and the decision is made by majority voting of M devices. For example, if you have a 2 out of 3 architecture, we will have 3 devices, and the evaluation of the safety function is only considered if 2 of them agree. Type A and Type B relate to the complexity of an element or a system. A simple electrovalve cannot be compared in terms of complexity with a multi-channel protection system. Therefore, the standard provides distinction between simple and complex devices and takes this into account when calculating the safety properties. IEC61508 defines, as we saw, 2 possible ways of certification, by design or by proven in use. Depending on the type of certification, different routes are offered. Routes 1H and 1S relate to certification by design, while routes 2H, 2S, and 3S relate to design by proven in use. The subscript H is for hardware safety integrity, while the subscript S is for systematic safety integrity. The failure rate is the number of failures that I can have for a component, element, or system per unit of time. We have different types of failure rates, depending, of course, on the type of failure. We can have failures that are considered safe, in the sense that they will result in a spurious trip of the machine, but without safety consequences. The same with those failures that are dangerous, but that I can detect by means of the internal diagnostic of the safety system. And then we have the most critical type of failures, the dangerous undetected failures. These ones will impair my safety system, meaning that the safety function or safety state are no longer guaranteed. The different failure rates will give us the safe failure fraction and, along with the other architectural dependent factors, the probability of failure of my system. The probability of failure can be expressed as probability of failure by demand when operating in low demand, PFD, or by probability of failure per hour, PFH, when operating in high demand mode. Now, as we saw, there are dangerous undetected failures that can impair our safety. These failures are in fact a ticking bomb. The probability of failure increases with time, and if we don't do nothing, the system will become sooner or later unsafe. Of course, functional safety takes this into account as well. The proof test coverage, PTC, will tell me how many dangerous undetected failures I can detect with a certain proof test. And the proof test interval, PTI, will tell me how often I should perform this test to maintain my average probability of failure under control. Let's look into an example. Here you can see how dangerous undetected failures, PTC and PTI, will affect our system. As time goes by, the probability of failure will increase and eventually render your system unsafe. And even if you do a proof test every year with a certain proof test coverage, let's say 50% in this example, at a certain moment your system will no longer comply with SIL2. As you can see, the average probability of failure is higher than the desired SIL level. In this case, one option that you have is to do a more comprehensive test, let's say with a coverage of 90%. Another alternative, very useful for equipment that is harder to test, like sensors, is to keep a simple but more regular test with a lower PTC, 50% in this example, and complement it with a more comprehensive test, let's say every 5 years, with a proof test coverage of, for example, 99%. This way you will keep your average probability of failure under control and still compliant with SIL2. As we all know, even when 100% tested, electrical and electronic components will age, and there is always a limit to the operational life that we can consider. Therefore, the standard has specific rules for cases where very high proof test coverage values are stated. The standard takes also into account the maximum mission time of a device for all PFD average calculations. Let's now take a look into SIL certificates. There are many certification bodies that can release a certificate of conformity, and all follow the same rules. When a certified body provides a formal certification document, this document, according to IEC61508, which is the standard that regulates conformity assessments, must contain a well-defined set of information. This set of obligatory information is not very extensive. Basically, it must contain the names of the certification entity and the customer, the product reference, the scope of certification, dates, and so on. Then some entities provide more information, others less. We can see here in this example the client name, certification body address, validity dates, and information regarding the standards to which conformity is stated. This is the minimum set of information that you must find in a certificate. Then you may or may not have more additional technical details depending on the certification body template. In this case, it is set SIL2 type A HFT0, so we know that it is a simple device without hardware fault tolerance, SIL2. But as you can see, there is still a lot of information we don't have. What about systematic capability? What about failure rates? What about proof tests? And this is the first thing you need to have in mind when reading a certificate. The conformity certificate is only part of the story. You need a safety manual to have a complete understanding of the safety properties of any device. So to learn the safety properties of the device, you must consult the safety manual, where you will find all the parameters that you will require to construct your safety instrumented function or system. You will find in the safety manual all the details: SIL level, systematic capability, architectural constraints, failure rates, and etc. Let's look now into another example and dig a bit further into the safety properties of another product. As we can see here, the certification body displays more information in the certificate itself than what we saw in the previous example. Note that this is not right or wrong. As long as the minimum information is there, it is okay. You always need to see the safety manual to have the complete figure. The safety manual is, as I said before, a crucial part of the certification. Let's look a bit into the safety properties again. You have low demand, type B, so a complex system, no hardware fault tolerance, and roots 1H and 1S. That means certification obtained by design. Then we see systematic capability, SC3, and just after the different failure fractions, you can read fit for use up to SIL2 HFT0 and SIL3 HFT1. What does this mean? Well, for systematic capability 3, we know now that this means that all the systematic failure avoidance measures are compliant up to SIL3. So all the development processes and so on are sound. But to use it in a SIL3 application, I must have at least an hardware fault tolerance of 1, meaning that I need to have at least 2 devices in parallel. This is what it's meant by this note on SIL2 or SIL3, depending on the HFT. The safety manual will provide additional details. By looking into it, we can see that if you need only SIL2, you can use only one device. However, if you need SIL3, you will need 2 or more devices in a configuration 1 out of 2 or 2 out of 3. That will give you the required hardware fault tolerance of 1. Let's look now on another example. In this case, we will see how low demand and high demand can be fulfilled by the same product, with, of course, and as we were expecting, some architectural constraints. As seen in other examples, you can see all the obligatory information in this certificate, and also systematic capability, type of element, SIL level, etc. But note what is said regarding demand modes. In the previous example, HFT1 would allow us to increase the SIL level. In this case, it will allow us to do something different. It will allow us to use the device in low or high demand modes, depending on the HFT or number of elements in parallel that I have. We have just discussed the basic principles of functional safety and very briefly functional safety standards, in particular IEC61508, and we took as well a look into some SIL certificates and user manuals. It means that we should now be able to answer to a few common questions about functional safety and SIL. It is just a paper? No, I think we just saw all the work that is involved behind the SIL certification and behind the design of a SIL product. It just requires more documentation? Certainly not. It requires specific implementations. It requires specific measures and tests and tools that we would not use if we would not be designing a system specifically for safety. A SIL product is always better than a non-SIL one? No, not necessarily. A SIL product shall only be used when we really need a SIL product. The reason is that a SIL product will be more expensive or it will have a higher spurious trip rate, for instance. Proven in use is better than by design or vice versa. The functional safety standard gives similar attention to both methods. It is the set of safety properties that matters at the end. Of course, a product certified by design tends to be more advanced and less prone to become obsolete or not supported anymore. Proof testing is just a test to see if my safety system is working well. As we saw, the proof test is a very specific test that is designed to cover undetected dangerous failures. It means to detect failures that are not covered by the internal diagnostics of the system. So it's not to see if my system works well, it's rather to see if my system will work well when I will need it. Is SIL a property of an element or a device? The correct interpretation of SIL is the capability to implement safety functions up to a certain SIL level. So it's not a property of the element by itself. It's this capability to be used in safety, to integrate it in safety instrumented systems to implement safety functions. Is it a design feature? No, as we saw, it goes well beyond the design itself. Systematic capability is a limiting factor. Certainly, yes. We saw it in one example that systematic capability is for sure a limiting factor. A longer proof test means a better safety system. This is a very common question and is even used sometimes as a marketing argument, but it is not necessarily true. A longer proof test interval can mean that we have more complex proof tests that we cannot implement easily. But most importantly, it can also mean that we will have a higher spurious trip rate due to the fact that we will have more dangerous detected faults. So it's not alone, it's not an indication of a better system or a worse system. It's the ensemble of all the safety properties that will tell us if the system is good or not. Are safety and reliability the same thing? It depends a lot on what you mean by reliability, but a system can be safe and not reliable. For instance, if it can have a lot of spurious trip faults, but it will always fall into a safe state, so it's safe, but it's certainly not reliable. On the other hand, a system with very low diagnostics will be more reliable, but less safe. HFT means redundancy? No. If you take the example of a 2 out of 4 architecture, you will have HFT of 2, but the redundancy, in fact, it will be 3. In a safety measurement chain, I can simply replace one element by another similar element from a different model or vendor, as long as it has the same SIL level. No, you need to check all the safety properties to make sure that you can replace. Remember that SIL is a range of values. This risk reduction effectiveness, for example, for you can 1 to 10 or 10 to 100 and so on, it's a range of values. So you can be replacing a product that has a very high effectiveness, so a very low probability of failures, by another that has a higher probability of failure within the same SIL classification. But when put together with other elements, will render your system more prone to fail. So it may force you to go to a lower SIL level. So you need to check all the safety properties to make sure that you can replace one system or one element by other. And you need, of course, to redo all your safety calculations. Can I increase my SIL level via redundancy? Maybe, not always. Your limiting factor is the systematic capability, as we saw. And the only way you can increase the systematic capability, and you can only do it by one, is by using a diverse redundant system in a dual channel architecture. But more than that, you will always be limited to the maximum systematic capability level that you have on your chain. So, thank you very much for listening, and we will now take any questions you may have.